We shall continue with the topic of chromatography. We were talking about the ion exchange chromatography, that is the chromatography used when you want to separate ionic metabolites or ionic proteins. It could be an anionic, it could be cationic, or it could be both together. So what happens in an ion exchange chromatography? We have an inert support. Nowadays they use more of a polymeric based support. You have ions, say in this particular example we are showing positive ions all anchored onto the inert support. Now suppose you are introducing a mixture of cations and anions, what will happen? The negative ions will bound to the positive ions, so the exhaust stream will have only positive ions coming out. Once you have done the separation, but you can change the buffer conditions, like you can change the salt concentration or you can change the pH, so that whatever negative ions that are bound will come out. So this is one way of separating positive and negative ions. Suppose you have both cations and anions anchored to the support, then we can remove the entire salt from a mixture. For example, I am using salt for salting out of protein. Such a solution will have protein and salts, and ion exchange chromatography containing both cations and anions could be one way of removing the salts first, and then you can go into purifying the protein of interest. So ion exchange chromatography is based on the concept of the ions, separation of ions. Either it could be ions of interest which could be concentrated, or ions of not interest could be captured. So both can be adopted. So the stationary phase will have ligands of certain charge, okay. So the biomolecules in the mixture of opposite charge will preferentially attach to it, and proteins or molecules with the same charge will be eluting out. Even uncharged proteins will be eluting out first. Now you can have two types of ion exchange chromatography, that means cation as well as anion, or you can have mixtures of both cation and anionic ligands present inside the chromatography. So for example, if you are looking at an anion exchanger, the functional groups used could be aminoethyl or quaternary ammonium. So there will be a plus charge on the nitrogen, okay. For cation exchangers we can have functional groups like carboxymethyl, sulfopropyl, methyl sulfonate, and so on actually, okay. Sulfonic and quaternary ammonium groups form strong, while other groups form weak ion exchangers. So if you are varying the ionization as a function of pH, it determines the strength of the ion exchanger. It does not tell you anything about the strength of the binding of the protein and the ligand, okay. It just tells about the strength of the ion exchanger system. So the interaction between protein and the ion exchanger depends on the net charge. So higher is the charge, higher will be the binding capacity. Charge distribution on the protein surface, okay, how the positive and negative charges are distributed on the protein surface, ionic strength, pH of the solvent, nature of ions that are present, and presence of other additives that are present inside. Higher the charge on the protein, more strongly it will bind to a given ion exchanger of opposite charge, obvious, right. Also the pH of the solvent determines the protein binding. It also determines the effective charge on the protein and ion exchanger. So if the protein has very high charge, it will bind strongly to the ion exchanger system, and if the pH of the solvent is different, then the protein binding capacity also becomes different. So what does an ion exchanger contain? It consists of a matrix, that is an insoluble matrix, that will be the base on which the ionic ligands are immobilized through a covalent bond, okay. The charge groups could be acidic, or the charge groups could be basic functional groups. So you can have four types of matrices. You can have synthetic hydrophobic polymeric resins like polystyrene. Polystyrene is pretty hydrophobic. Natural or synthetic hydrophilic polymers. So when you say natural, it could be cellulose, dextran, agarose, and so on. It could be synthetic hydrophilic polymers made into hard beads like they use in HPLC systems. So what is the advantage? We can use rigorous methods for washing and cleaning, recycling, reusing, so that is an advantage, or we can use silica gel based method. So you can have different types of matrices in an ion exchange column. So a typical ion exchangers, if you have a cationic exchanger, I could use carboxymethyl, we can use orthophosphate, we can use sulfonate, we can use sulfoethyl, sulfopropyl and so on. So each one has different pK values, okay, as you can see here. So depending upon the type of ions you would like to separate, then we can use different types of cationic ligands anchored to the stationary phase. Suppose we are looking at anionic, we can use diethyl aminoethyl, trimethyl hydroxypropyl, quaternary aminoethyl, triethyl aminoethyl, polyethylene imine. So you see a lot of nitrogen containing groups are here in most of this, okay. So that is how you get the charge, N plus charge, okay, whereas in the previous case we have a lot of OH type of groups which gives you a negative charge. Again if you look at the pK values, they are more in the basic side, whereas in the other case they are more in the acidic side. So what determines the capacity of an ion exchanger? Capacity is the quantitative measure of the ability of the ion exchanger system to take in the counter ions. So it depends on the number of charged functional groups present inside the column per gram of dry ion exchanger per ml of swollen gel. So how do you determine it? We can titrate it with strong acid or base, and then we can find out how much of the acid or base required to neutralize the ion exchange system, okay. So you can have say like 100 to 500 micromolar per ml of beads, you know, beads of bed. So that is a very high degree of ionic capacity. So the total capacity of an ion exchanger for binding protein can be expressed in terms of serum albumin for anion or lysozyme or hemoglobin for cation exchangers. So generally the capacity is based on, if it is an anion, the amount of serum albumin that can be exchanged, if it is an cation, the amount of lysozyme or hemoglobin that can be exchanged. So the properties of ion exchange will depend on porosity as well, because highly porous material we can have more charged ligands bound to it. Type of charge functional groups present on the stationary matrix, number of charge functional groups present on the stationary matrix. So all these properties decide on the ion exchange matrix. So how do you get high capacity in an ion exchanger matrix? We can have highly macroporous matrix, we can substitute it with ionic groups which maintain their charge even over a wide range of pH, that is also very important. So greater the pore size of an exchanger, greater will be the dynamic capacity for a given protein. For example, if you take DE, AE, Cefadex, A50, which has large pores, binds about 250 milligrams of hemoglobin per ml of bed. That is a big number, 250 milligrams of hemoglobin per ml of bed. Whereas if we have a A25 with smaller pore, it binds only 70 milligrams of hemoglobin per ml. So we can achieve 250 milligrams of hemoglobin per ml, or we can achieve 70 milligrams of hemoglobin per ml depending upon the pore distribution and pore size. Non-porous matrix will have lower capacity than porous matrix, that is obvious, but non-porous matrix will have higher efficiency because the molecules do not have to diffuse through the pore, so the pore diffusion is 0, so it is having less diffusion distances, so capacity will be higher. For a cation exchanger, the buffering ion should be negatively charged, okay. like phosphate, carbonate, acetate or morpholin sulfonate when the counter ions is ammonium, sodium or potassium. So ammonium acetate is used for cation exchangers because it has the additional advantage of volatility, and whereas for an anion exchanger the buffering ion should be positively charged, like tris buffer with chloride as the counter ion. So if you have a cation exchanger, the buffering ion should be negatively charged. If you have an anion exchanger, the buffering ion should be positively charged. So for a cation exchanger, the buffering ion could be phosphate, carbonate, acetate, morpholin sulfate when the counter ions are ammonium, sodium or potassium, correct. Whereas if it is an anion exchanger, we could use tris buffer with chloride as the counter ion, because for an anion exchanger we need a positively charged buffering ion. So how do you go about preparing the sample? For an anion exchanger we need to prepare the sample. So the amount of sample should be less than 20% of dynamic capacity of the bed, and sample volume should be less than 5% of the bed volume. So we do not want to overload the bed, then it becomes very inefficient. The sample should be free from suspended particles or turbidity, because we do not want turbid material binding to the ions. Viscosity of the eluent and the sample should be similar. If the eluent and that is the continuous phase and the sample are different, then you are going to have problems with the flow. So in case of nucleic acid samples, viscosity may be reduced by digestion with the endonuclease. Syringe introduction of sample is always recommended. Column should be washed with the starting buffer till no free or unbound components are present in the column. So we have to keep washing until whatever is bound gets totally removed and the column is free from any ions bound to the ion exchanger. So even after each analysis or after each separation, we need to wash the column thoroughly using a buffer solution. So variety of elution techniques can be used. We can use an isocratic elution, that means we use a single solvent, single strength continuously flowing throughout the separation process. We can use stepwise elution, that means we can slowly change the strength of the salt in terms of steps. We can have a gradient elution by changing the pH or ionic strength or both, that means we can slowly linearly change the pH over a period of time. We can have affinity elution, that means we can add certain affinity ligands. We can have displacement chromatography, that means we can have another buffer solution which will displace whatever has been bound to the ion exchange column. So we can think of different elution techniques for separation as well as for later activation of the column, as well as removal of ions which are bound to the stationary phase. So the column regeneration is a very important aspect after you have done the ion exchange separation process. Like I mentioned that you need to keep on washing with buffer until whatever is bound gets removed. So like a salt solution, okay. So we can introduce salt solution until the ionic strength reaches about 2 molar to wash out whatever has been bound to the ion exchange stationary matrix. So the salt solution should contain counter ions to the ion exchanger to facilitate equilibration. That is very important actually, okay. So there should be some counter ions which will remove the ions that are bound to the ion exchange matrix. Sometimes denatured proteins or lipids may remain in the column even after regeneration, okay. There may be some tightly bound impurities. So what do? Then we have to removal of tightly bound impurities or denatured proteins by washing the column with 0.5 to 1 molar sodium hydroxide solution. No? So we have to resort to very harsh conditions like using sodium hydroxide, okay. So it will remove all the contaminants, number 1. Number 2, it will also inactivate if there are any microbes present, so that way we are something like sterilizing our system, so that the microbes do not grow and form biofilm inside your ion exchange system. So what are the column material or the stationary phase we need to consider? The column material should be inert, the bed support should facilitate free flow of liquid with minimum clogging, okay. That is very important. If you are going to have a clogging, you are going to create pressure inside the column and you are creating a back pressure. So the pump which is pumping the solution inside is going to have problem, and the column material should be easily replaceable, and then so that we can charge with fresh material inside. It should withstand back pressure developed when high performance medium is used, that means it should not crumble when we apply very high pressures. The dead space inside the column after you have packed should also be minimum, okay, because if you have dead space we are going to have improper mixing. So we will have zones of good mixing and good separation, you will have zones of improper mixing and bad separations. So the uniformity of separation is going to be very poor. So there should not be any dead space inside your packed column. So these are certain requirements for the column material, and hence you need to design column materials so that all these conditions are satisfied. The column length should be 5 times the diameter of the column, okay. Short column is preferred for gradient elution, while long column is preferred for isocratic elution. So if you are thinking about only isocratic, that means using only one solvent of certain strength throughout the chromatography process, then it is better to have very long column actually. So generally if you look at laboratory column, they will have a packed height varying between 5 to 15 centimeters. 15 centimeters is almost half a foot, so it is not very long actually. And the amount of ion exchanger should be 10 to 20% of its dynamic capacity, okay. Anion exchange systems are used quite a lot in hard water purification, especially for purification of well water or river water which contains too much hardness. Hardness is caused by the presence of calcium and magnesium ions, so it forms insoluble precipitate just like soap actually. So we can soften the water, we can soften the well or deep bore well water using an ion exchange system. We can use sodium ions so that the calcium and magnesium are replaced with sodium ions. So ion exchange systems are the best if you want to soften water. The column must be regenerated of course by passing concentrated solution of sodium chloride. So we cannot keep on using the same column for processing large amount of hard water. After some time the calcium and magnesium ions will completely saturate the ion exchanger, so we need to pass sodium chloride. So what will happen, excess sodium ions will displace this calcium and magnesium ions that are bound to the stationary matrix. So originally these type of stationary phases were made up of natural aluminum silicates, but then long term stability of these inorganic material were not as good as synthetic polymeric resins, because synthetic polymeric resins can survive much harsher conditions, can survive much longer duration of operation and also several cycles of operations. Now having talked about ion exchange, let us move to the next type of possible separation, that is based on the differences in the hydrophobicity. So proteins have hydrophobic and hydrophilic groups present on the top. So sometimes the hydrophobic groups may be embedded inside, then such groups will not be able to contribute in the separation process, but sometimes these hydrophobic groups may be present outside because of the folding of the protein. So generally hydrophobic groups are inside because proteins are always present in aqueous environment which is hydrophilic, so hydrophobic groups are always present inside, but at some time because of the folding constraints these hydrophobic groups are present outside. So proteins may have different patches of hydrophobicity, and this particular property is made use of in the area of hydrophobic interaction chromatography. So how does it happen in this particular chromatography? We have the matrix with hydrophobic groups. So suppose you have a mixture of proteins with hydrophobic and hydrophilic nature, then what will happen? All the hydrophobic proteins will bind to the hydrophobic matrix, the hydrophilic proteins will be eluted out first. Later on we can change the buffer, or we can add a detergent, or we can add a salt, or we can add solvent and so on, so that whatever is bound, the hydrophobic proteins bound gets released and they come out. So initially we will have predominantly hydrophilic proteins, and later on during the regeneration we will have hydrophobic proteins. So this is a good way of separating these two type of proteins. So this is based on the hydrophobic nature of the on the surface of the protein. So more hydrophobic it is, more bound it is going to be, less hydrophobic it is relatively, it is going to come out first. So all proteins will have hydrophobic groups, but the problem is mostly these hydrophobic groups are embedded inside. So it is like the hydrophobic amino acids, that is those with non-polar R groups like alanine, phenylalanine, valine, tryptophan, leucine, isoleucine, methionine and so on. Even phenyl groups, hydrocarbon chains, they all contribute towards the hydrophobic interaction part of it actually. So a lot of these groups lead to the hydrophobic nature of the protein. So generally, as I said, in an aqueous environment these are buried inside the protein, but sometimes non-polar amino acids are located outside due to the folding constraints. Okay. So if you have proteins of different hydrophobic surfaces, then you can separate out using this hydrophobic interaction chromatography. Okay. So what does the process involve? It involves loading a protein mixture suspended in a high salt solution onto a matrix containing hydrophobic matrix, eluting the protein by decreasing the salt in the solution. Okay. So what are you doing? You are reducing the salt, so the protein will go more into the solution, okay, and they get bound to the surfaces depending upon the extent of hydrophobicity. Later on we will change the polarity of the phase by adding non-ionic detergents or organic solvents. During the process, whatever hydrophobic proteins that have been attached to the hydrophobic matrices will get released. So these are the various steps in the entire process of hydrophobic interaction chromatography. So it can be used in the early stages of the separation processes, especially when the protein is precipitated in the presence of salts. Okay. And also it uses high salt concentration, you are using very high salt concentration. So this method is ideal if the previous method also uses salt. So you do not have to remove the salt as a step 1 and then go for some other chromatography, because some chromatographies will be hindered if the salts are present, whereas HIC will work only in high salt concentration. So this is a very good technique, and HIC, ion exchange chromatography, gel filtration chromatography, that is GPC, they are useful to remove protein without affecting its activity. So when I use HIC I am not affecting the activity of the protein. If I use ion exchange chromatography I will not be affecting the activity of protein. If I again use gel filtration or gel permeation chromatography I am not affecting the activity of the protein, whereas some techniques may affect the activity of my protein. So HIC is ideal for such situations. Okay. So what are the important parameters we need to consider when we are using HIC type of separation? Type of ligand. okay, what type of hydrophobic groups am I using on top of my stationary matrix, what is the percentage coverage of these ligand on the matrix, composition of the matrix support, what is the type of salt used in the buffer, concentration of the salt, what is the pH, what is the temperature, what are the additives used in the buffer, are you using any other chemicals to change certain surface properties, or are you using some chemicals to change dielectric constant of the solvent, and so on actually. So these are the parameters which is going to affect the performance of the HIC. So we can play around with these parameters so that I am able to get a good separation in a mixture of proteins based on HIC. So what are the type of ligands that are immobilized on the stationary phase, okay. So because that determines the selectivity quite a lot. We can think about groups like alkyl groups of different chain lengths, because alkyls are hydrophobic, so we can have different chain lengths alkyl, and thereby I increase the hydrophobic nature of the groups. Or I can use aryl groups like phenyl groups, they are also hydrophobic in nature actually, okay. So I can have surfaces with the different alkyl chain length attached, which makes the surface hydrophobic in nature. So if I have very long chain hydrocarbon, then the binding capacity will be much higher when compared to short chain hydrocarbons. So the ligands that are immobilized are generally hydrocarbon chain lengths or aryl type of groups. Common matrices used in hydrophobic interaction chromatography are about 4 to 6% cross-link agarose, but they are strong hydrophilic carbohydrates, okay. Smaller particle size will lead to higher resolution, so like 34 micron particles will lead to very high resolution, but you need to consider that the pressure drop in the column will be inversely proportional to the square of the particle size, that is pressure drop is proportional to 1 by particle size square. So smaller the particle, higher will be the pressure drop, and it is going to go up in terms of square. So if the particle size goes down, pressure drop increases, the pressure drop increases, back pressure increases, that means I need to have much more stronger pump to pump the solution through the column. So that is a big problem. So you need to consider this aspect, and you cannot keep on reducing the particle size of the support. Addition of salts lead to salting out. We talked about salting out long time back. So more salts you have in the solution, protein will start coming out, and it will increase the interaction between the protein and the ligand, okay. So the idea is to increase the interaction between the protein and ligand. So what you do, you can add lot of salt. If the concentration of salt is increased, the amount of protein bound to the immobilized ligand also increases. It is obvious, when I am adding more salt, I am enhancing salting out, so the proteins are going to precipitate out. Now these proteins will interact more strongly with the ligand. So salt promotes interaction, whereas some salts promote elution of the protein from the matrix. That means some salts can also help in the displacement of the protein bound to the matrix. So there is something called Hofmeister series which describes the effect of anions and cations on protein precipitation, okay. So if you move from this end, right hand end, right going to the left hand end, we are increasing salting out effect. This is also called structure forming. So if I am moving from SCN minus to I minus, ClO4 minus, NO3 minus, Br minus, Cl minus, CH3COO minus, SO4 2 minus, PO4 3 minus, I am enhancing the salting out, okay. Whereas conversely, if I am moving from this end to this end, I am increasing the salting in effect, that is called catastrophic. So if I am moving from ammonium 4 plus to Rb plus, K plus, Na plus, Cs plus, Li plus, Mg2 plus, Ca2 plus, barium 2 plus, I am increasing the salting in effect. That means protein will dissolve more inside the solution. So if I am moving from here to here, that is from the right to the left, I am enhancing the solubility of the protein, or sorry, I am enhancing the salting out effect, that is protein will be coming out, whereas if I am moving in from this left hand end to the right hand end, I am enhancing the salting in effect. So this type of movement will enhance the interaction between the protein and the immobilized material, whereas when I am moving from this end to this end, I am increasing the solubility of the protein inside the solvent. So I am decreasing the interaction between the protein and the immobilized hydrophobic group. So you can play around with the type of anions or with the type of cations, either to enhance the interaction between the protein and the ligand which is immobilized through hydrophobic interactions, or I can reduce the interaction between the protein and the ligand. So changing pH also improves interaction between ligand and matrix. So we can play around with pH so that we can enhance the interaction. For example, a ligand that do not bind to a hydrophobic interaction stationary phase at neutral pH may bind at acidic pH to it, okay. So I can make it slightly more acidic so that I can make the protein bind to the stationary phase, whereas it might not be binding at the neutral pH. Okay, once you have bound this protein, the next step will be regenerating the column and recovering this bound protein, right. That is called desorption, recovery, collection of whatever has been bound to the matrix. So what do? We decrease the concentration of salt. So when we decrease the concentration of the salt, what happens? There is something called salting in that may be happening. So the protein that is bound to the hydrophobic matrix will go into solution in the solvent. Originally we had very high concentration of salt, so we had a salting out like effect. Now we will have lower concentration of salt, so we will be having something called a salting in type of effect. We can add an organic solvent. So what are you doing? We are changing dielectric constant of the elution buffer. So we can add an organic solvent, we are changing the dielectric constant, so the protein that is bound will get unbound. We can also add neutral detergent, that means detergent is nothing but surfactant. So by doing this we are trying to solubilize the protein that is bound to the surface. So these are some techniques by which we can recover the protein that is bound to the immobilized surface when we perform an hydrophobic interaction chromatography. So at the same time you are regenerating your column for further studies, okay. So different ways, one is changing the concentration of salt, second is by adding an organic solvent, changing the dielectric constant, or adding some detergent, neutral detergent. We do not want to add a cationic or anionic type of detergent, because that is again going to contribute in the form of changing the concentration, but we want to add a neutral detergent. So decreasing the concentration of the salt, we can do it in a linear or stepwise manner. So we have a very high concentration of salt, so we can slowly decrease in a very linear fashion over a period of time, or we can decrease it in steps, 2-3 steps, the concentration is brought down. So in a continuous gradient, salt concentration is decreased linearly or continuously. In step gradient, one or more salt solutions of discrete concentration are passed through the column. Stepwise elution is preferred for large scale operations, because doing a very uniform reduction in salt concentration over a period of long time might not be possible, whereas we can go down in steps, which is much simpler, easy to perform. We can even reproduce it after 1 hour I reduce the salt from some value to half the value, then after another 1 hour I may be reducing the salt concentration from that to lower value and so on. So we can do this type of strategy for the recovery of the bound protein. Water as an eluent also has been tested, that also helps in desorption of the protein that is bound. So adding low concentrations of water miscible alcohols, detergents, salts like catatropic salts that decrease precipitation of hydrophobic compounds weakens the protein ligand interaction. So this is another way. First method we looked at is changing the salt concentration, but here we are talking about adding some solvents like alcohols, detergents, that is surfactants, or even salting in salts and so on actually. Now all these when you do, you are desorbing the protein that is bound to the matrix. So these techniques help you to regenerate your column as well as recover whatever has been bound to the column. Now if you look at a normal interaction chromatography, so you have a polar stationary phase, okay. So you have your protein, there are polar groups here, so there is an interaction between the polar group of the protein and the polar stationary phase. So you will be using a non-polar solvent here, so hydrophobic proteins will come out first because there is no interaction between the hydrophobic proteins and the polar stationary phase, for example like silica or something, and the polar proteins, because they are going to interact with the polar stationary phase, will get retarded and they will come in the end. Whereas if you have non-polar stationary phase like hydrophobic stationary phases and you use a polar solvent, what will happen? Hydrophobic proteins will interact more with the non-polar stationary phase, whereas hydrophilic proteins will not interact, they will be coming out first, and the hydrophobic proteins will be retarded, they will get slowed down, they will come slowly later. So in an interaction chromatography where you have a polar surface and a non-polar solvent, the hydrophobic proteins will come out first, the polar groups and polar proteins will come out later. Whereas if you take a hydrophobic type of interaction system or a reverse phase chromatography, you will be having a non-polar stationary phase, you will be using a polar solvent, so the hydrophilic proteins will come out first because it is not going to interact with the stationary phase, whereas the hydrophobic proteins will come out in the end because they will be interacting with the stationary phase. So two types of approaches, we can use a polar stationary phase and a non-polar solvent, or we can use a non-polar stationary phase and a polar solvent. So both can be used depending upon what you want to recover, what you want to separate, what does the mixture contain, what is the concentration of the protein of your interest, cost factors, time factors, so on actually, you know. So this hydrophobic system can be also called reverse phase chromatography, because in a normal phase we use a polar stationary phase, whereas in a reverse phase we are using a non-polar stationary phase, like a hydrocarbon, like aryl group, long chain hydrocarbon. So even in high performance liquid chromatography we use a hydrophobic stationary phase or a reverse phase. So this interaction chromatography, we have a polar stationary phase such as silica gel and non-polar solvents such as hexane. So there is an interaction between the polar functional groups in the protein and the polar groups on the stationary phase like NH, OH and so on. So low polar substances are eluted first and then followed by increasing polarity. So whereas in the reverse phase or hydrophobic system, the stationary phase is a non-polar and the elution is done through a polar solvent. So polar solvents will elute out first, non-polar components will elute out at the end. So the elution sequence for reverse phase will be carboxylic acids, amines, sulfones, sulfoxides, alcohols, amines, esters aldehydes, ketones, nitro compounds, ethers, sulfides, aromatics, organic halogens, olefins, and finally alkanes. So for a reverse phase, alkanes will come out in the end because there is going to be an interaction of alkane with the non-polar functional groups present on the stationary phase, whereas the carboxylic acids which are polar in nature will not interact and they will come out very fast. Okay. Sometimes surfactants are also used in the mobile phase in liquid chromatography because they are very good in solubilizing hydrophobic compounds. They can help in partitioning many solutes into micelles. They are very low cost. They can also change the polarity of the mobile phase, okay, depending upon the type of surfactants we use. So that is why surfactants are also used in liquid chromatography systems and they have quite a good advantage. So what are the critical parameters we need to consider in reverse phase? The column length, how long you want to have the column, flow rate of your continuous phase, what is the temperature you are working at, what are the solvents you are using, because I said you generally require a polar solvent because you are using a non-polar or hydrophobic stationary phase. Ion suppression, how are you preventing the suppression of ionization, because once you have ionization then the hydrophobic interactions will not take place. Ionization spoils this type of hydrophobic interaction. So what do? We need to change the pH so that ion suppression is taking place. That means there is no dissociation of the compound into ionizable species. Use of ion pairing agent. So all these parameters can help us to manipulate the process or the efficiency or the selectivity of the reverse phase chromatography. Okay. Higher molecular weight biomolecules can be purified on short column. Increasing column length improves the resolution only marginally, whereas if you have small peptides, increasing column length improves the resolution. Resolution of large biomolecules is insensitive to flow rate, and flow rates with long columns may decrease resolution due to increased longitudinal distance. So they have to travel a longer distance in a long column, so the resolution gets decreased. So in a hydrophobic or the reverse phase system, the higher molecular rate biomolecules can be purified in short columns. Increasing the column length is not going to improve your resolution, whereas if it is small peptides, yes, we can improve the separation with longer columns. And resolution of larger biomolecules is also insensitive to flow rates. Okay. And flow rates with long columns will decrease resolution due to increased longitudinal distance as they travel longer distance. So for low molecular weight solutes, temperature has a bigger effect, because if I increase column temperature, I am affecting the viscosity of the mobile phase. When I affect the viscosity of the mobile phase, I am affecting the diffusions, I am affecting the dispersions, I am affecting the flow patterns. So that will have a bigger effect, because mass transport of solute from the mobile to the stationary phase is a diffusion control process. So when I am affecting the viscosity, it is going to affect my diffusion coefficient. So decreasing solvent viscosity will improve mass transfer coefficient, leading to a better resolution or higher resolution. Now we talked about the hydrophobic interaction chromatography. We also mentioned about the concept of reverse phase chromatography. Originally before that we talked about ion chromatography. Now let us move to the next type of chromatography. This is called gel permeation chromatography or size exclusion chromatography. So it is based on size or it is based on molecular weight, assuming higher molecular weight are bigger in size. For proteins, higher molecular weight are bigger in size, smaller molecular weight are smaller in size. Okay. So what do you do here? We have stationary phase with pores. So small molecules which are smaller than the pores will diffuse inside the pores, get entrapped and get slowed down, whereas large molecules which cannot enter the pores will keep travelling, so they will rapidly come out on the other side, they will exit faster. So large molecules will come out faster, small molecules will take much longer time to come out. So the elution time is inversely proportional to the size of the molecules or molecular weight of the molecule. So it is a very good technique to separate molecules of different sizes or molecules of different molecular weights, and it is called size exclusion chromatography or gel permeation chromatography. So what happens? We have porous matrix inside, we have big proteins, small proteins, or proteins with higher molecular weight or proteins with smaller molecular weight. So as they travel, the smaller proteins get entrapped in the porous material, so larger proteins will just come out, and after some time all the larger proteins have been removed and the smaller proteins will come later. So elution time is inversely proportional to the molecular weight or size of the proteins. So the small molecules get entrapped in the porous, large molecules cannot enter the pores, so they travel faster. That is the principle of gel permeation chromatography or molecular sieve type of chromatography. Okay. So typically if you are looking at elution volume or elution time, you may have a 660,000 molecular weight material coming out fast, followed by 400,000 molecular weight material, followed by 150,000 molecular weight material, 55,000 molecular material, 40,000, finally 10,000. So you can see that a molecular weight from 660,000 to 10,000 could be nicely separated out using this gel permeation chromatography or size exclusion chromatography. So it is extremely useful for separating out proteins. We can even measure the molecular weight of an unknown protein if we know molecular weight of certain proteins. So we can use it as a analytical tool, we can use it as a separating tool as well. So it can be used both in analytical chemistry as well as in purification area. So the stationary matrix for lipid is made up of copolymers of styrene and divinyl benzene. So it will have pore sizes in the range of 50 to 500 angstroms. So it will be of spherical particles of 5 to 10 micron in diameter. The mobile phase can be tetrahydrofuran, dichloromethane, toluene. So if you are talking about lipoproteins, biomolecules and so on, we can even use aqueous mobile phases. So this gel permeation chromatography can be used for proteins, biomolecules, it can be used for small molecules, it can be used for synthetic polymers, natural polymers and so on. As I said, it can be used for both purification as well as for analysis. Suppose I have a protein of unknown molecular weight, and if I have a few proteins of known molecular weight, I can get a standard graph between the elution time of the known proteins vis-a-vis their molecular weight, and if I get the elution time for the unknown protein from the original standard graph, I can calculate what will be the molecular weight of the unknown protein. So it is quite a powerful technique in the area of analytical chemistry, and it can also be used for purification based on the size or purification based on the molecular weight. What are the types of detectors we can use? We can use discometer type of detector, we can use low angle laser light scattering detector, we can use refractive index detector RI detector, we can use UV detector visible range, we can use fluorescent detector, we can use differential refractometry coupled with UV detection. So large number of detectors can be used depending upon the characteristics of the protein or metabolites or small molecule or synthetic polymers or natural polymers you are trying to separate out. So these supports are also similar to the supports that are used in ion exchange chromatography. and we can synthesize them with varying pore size, because this technique is totally based on pore size. Smaller pores will allow small molecules to get entrapped, larger pore will allow only large molecules to get entrapped. So if I have small pores, larger molecules will not be able to enter. So it is based on the concept of size. So we can synthesize pores of different sizes, okay. So the pore size is also a function of the density of the polymer and also the degree of cross linking, okay. So I can manipulate the degree of cross linking, I can manipulate the density and achieve different pore sizes. So we can even separate molecules as small as mono, di, trisaccharides, that is 100 to 500 Daltons also can be separated, going right up to mega Daltons, okay, like 10 power 6, 10 power 7 Dalton molecular weight. So this technique is very powerful for separating out from a very small range in terms of 500 Daltons going up to million or 10 million Daltons as well. So we will continue in next topic of chromatography in our next class.